Most people assume modern agriculture runs on chemical fertilizer because, well, nothing else has ever worked at scale. But, that assumption is not entirely true. There was a period quietly documented in agricultural research stations, wartime field trials, and post-war soil programs when scientists genuinely believed they had effectively eliminated the need for synthetic fertilizer using living soil bacteria. In controlled environments and even in some real farming regions, yields actually rose while fertilizer inputs dropped to nearly zero. Yet somehow the breakthrough never became standard practice. It faded from policy, from markets, and eventually from public memory. If you care about long-term food security, resilience under disruption, or how agricultural systems actually survive crises, that disappearance really does matter. Before we begin, subscribe to The Survival Record if you value historical analysis that looks past official narratives and into the decisions that shaped how we actually live today. The modern fertilizer system was born from war, not farming necessity. To understand why soil bacteria once threatened fertilizer use, you first have to understand why fertilizer became dominant in the first place. Synthetic nitrogen fertilizer did not emerge primarily to feed crops. It emerged to feed artillery. Industrial nitrogen fixation, the conversion of atmospheric nitrogen into usable compounds, became a strategic technology in the early 20th century because explosives require fixed nitrogen. When global trade routes fractured during major conflicts, countries that could not produce their own nitrogen compounds faced military vulnerability and food shortages simultaneously. This dual dependency shaped national policy. Fertilizer factories were built as strategic infrastructure. Agricultural productivity became tied directly to industrial chemistry. Food security and munitions production shared the same technological foundation. That system worked. It produced predictable yields, measurable outputs, and logistical control. But it also locked agriculture into a model dependent on centralized manufacturing, energy consumption, and distribution networks that behave poorly under disruption. Every major war and supply crisis since then has exposed that fragility. Researchers knew this, and many of them searched for a biological alternative. Scientists discovered that some soil microbes could replace industrial nitrogen entirely. Nitrogen fixation is not a human invention. It is a biological process that existed long before industrial chemistry. Certain bacteria convert atmospheric nitrogen into forms plants can use, forming symbiotic relationships with roots or living freely in soil. By the early 20th century, agricultural scientists had identified multiple species capable of enriching soil naturally. Some formed nodules on legumes, others operated independently, building fertility directly within the soil ecosystem. Laboratory results were promising, but field application was the real test. Researchers began experimenting with microbial inoculants, introducing beneficial bacteria into depleted soils to restore productivity without chemical inputs. The results varied, but under controlled conditions, something remarkable happened. Crops grew vigorously, soil fertility improved season after season. In some test regions, fertilizer application dropped dramatically, while yields remained stable or increased. For scientists working through wartime shortages and post-war rebuilding, this was more than an agricultural curiosity. It suggested the possibility of decentralized fertility, soil that could sustain itself biologically rather than industrially. That idea carried enormous strategic implications. Wartime shortages forced governments to take biological fertilizer seriously. During major supply disruptions, fertilizer production could not always meet demand. Transport bottlenecks, fuel rationing, and industrial prioritization forced governments to explore alternatives. Microbial soil enhancement programs expanded under these pressures. Agricultural ministries funded research stations focused on biological fertility. Extension services distributed bacterial cultures to farmers. Trials were conducted in regions where chemical fertilizer access was limited or unreliable. The motivation was practical. If soil microbes could maintain yields without industrial inputs, agriculture would become less vulnerable to blockade, bombing, or infrastructure failure. In some regions, the results justified the effort. Fields treated with nitrogen-fixing bacteria showed sustained productivity across multiple planting cycles. Farmers reported reduced dependence on external inputs. Soil structure improved. Long-term fertility stabilized rather than fluctuated with fertilizer availability. From a survival perspective, this was the agricultural equivalent of local water purification or seed saving, self-maintaining systems that reduced dependence on fragile supply chains. But large-scale adoption required consistency, and consistency proved difficult. Scaling biological systems, well, it turned out to be far more complex than scaling chemicals. Synthetic fertilizer behaves predictably because it's chemically uniform, but microbial life does not. Bacterial inoculants worked well under specific environmental conditions, things like particular soil compositions, moisture levels, temperature ranges, and crop rotations. But outside those conditions, performance varied. Sometimes it varied dramatically. Maintaining viable bacterial cultures during storage and transport posed yet another problem. Many early formulations degraded before they even reached farms, and others failed to establish themselves in soil ecosystems that were already dominated by competing microbes. Farmers, who were used to predictable chemical inputs, found biological systems much harder to manage. Success required understanding soil ecology, not just application rates, and that knowledge gap really limited adoption, even where the results looked promising. Industrial agriculture, you see, favors uniform solutions. But biological fertility is, by its very nature, inherently local. For policymakers tasked with feeding entire populations, this kind of variability looked, well, like risk. After the wars ended, industrial fertilizer, well, it regained its political advantage. When industrial production stabilized after those major conflicts, the fertilizer supply rebounded. Governments had invested heavily in chemical infrastructure, and industries built around nitrogen production gained real economic influence. Agricultural policy, shifted toward maximizing output through standardized methods. Now, biological programs didn't disappear overnight, but funding declined. Research priorities changed, and extension services began to focus on chemical optimization rather than ecological management. This wasn't necessarily a conspiracy, it was more like institutional momentum. Industrial fertilizer offered immediate, measurable results across diverse environments, while biological systems, well, they required patience, monitoring, and local adaptation. In the logic of post-war reconstruction and economic expansion, speed and scale mattered more than resilience. The soil bacteria never stopped working. They simply stopped being the central strategy. The disappearance of microbial fertilizer was gradual, technical, and honestly largely unremarked. There was no single moment when biological fertility was abandoned. Instead, programs were quietly reduced. Research merged into broader soil science, and commercial inoculants became niche products rather than national policy tools. Farmers who had used them often continued privately, and some regions preserved traditional practices that relied heavily on biological nitrogen cycling. But without sustained institutional support, the approach never became dominant. Public memory followed policy. Over time, synthetic fertilizer came to be seen not as one option among many, but as the only serious method of large-scale crop production. The earlier experiments faded into archival reports and specialist literature. What remained was a structural dependency that, frankly, few people questioned. Later, environmental crises forced scientists to reconsider what had been set aside. As the decades passed, the costs of intensive chemical fertilization became clearer. Soil degradation, runoff pollution, and long-term fertility decline triggered renewed interest in biological systems. Researchers revisited nitrogen-fixing bacteria, soil microbiomes, and regenerative agricultural practices. Many rediscovered principles documented generations earlier, evidence that soils could maintain productivity through biological processes if managed carefully. But rebuilding that knowledge base proved difficult. Agricultural systems had reorganized around chemical dependency, and infrastructure, training, and economic incentives all reinforced the existing model. Biological fertility required not just new technology, but a different philosophy of land management. That shift has always been harder than technical innovation. The deeper lesson here is about resilience, not just agriculture. From a survival perspective, the story of soil bacteria replacing fertilizer is not primarily about farming technique. It's about how societies choose between centralized efficiency and decentralized resilience. Industrial fertilizer provides scale, speed, and uniformity. Biological systems, on the other hand, provide sustainability, adaptability, and independence from fragile supply chains. In times of stability, centralized systems appear superior. But in times of disruption, war, embargo, energy crisis, infrastructure failure, self-maintaining ecological systems become strategically valuable. The historical record shows that governments recognized this during periods of emergency. They invested in biological fertility when survival required redundancy. When stability returned, they reverted to efficiency. That pattern repeats across many technologies, not just agriculture. Now, why can't you easily buy the fertilizer replacing bacteria today? The bacteria themselves still exist. They were never lost. What disappeared was the coordinated effort to make them the foundation of agricultural policy. Modern microbial soil products exist, but they operate within a system still structured around chemical inputs. They are supplements rather than replacements. Developing region-specific microbial systems at national scale requires long-term investment, localized research, and farmer training. That commitment competes with an entrenched industrial model that delivers predictable results quickly. In other words, the barrier is not biological feasibility, it's institutional structure. History shows that when survival demands change, institutions can shift rapidly. But without that pressure, existing systems persist, even when alternatives are viable. Remembering this history changes how we think about preparedness. The story of soil bacteria that once reduced fertilizer dependence is not an agricultural curiosity. It is a case study in how societies manage risk, dependency, and resilience. During crisis, nations experimented with biological systems that made food production less vulnerable to industrial disruption. They proved those systems could work under certain conditions. Then they allowed them to recede when industrial supply stabilized. Understanding that cycle matters. It reveals that many technologies we consider indispensable are historically contingent, not inevitable. Preparedness is not just about stockpiling resources. It's about maintaining knowledge of systems that function when centralized infrastructure fails. Biological soil fertility was one such system. Its partial disappearance reflects choices about efficiency, not limits of nature. Understanding overlooked histories like this helps us see the hidden assumptions shaping modern survival systems, how they formed, what they depend on, and how they might fail. If you value deep historical analysis that looks beyond official narratives, subscribe to the Survival Record and share this video with others who want to understand the foundations of resilience, not just its slogans.